Well, hi, thank you so much for joining me here today. Oh, look at this. I got these two guys out on my bench now. So I did a one-day wonder on the C3 capacitor checker. I got a really good result from it. It's back out here for a good reason. We're going to talk about this one first. And this guy, I'm all done with him. He's still here because I haven't put him away yet. But the two guys here on the bench, both of these having their own built-in power transformer, two-prong plug, unpolarized plug. I thought this would be a great chance to fool around with the two of them now in proper operating condition and fool around. That's why I have the power bar here, putting the plugs in this way and that way, measuring the voltages between the chassis, and just getting really clear on what's going on there. I don't think any surprises or mysteries will come, so we can be pretty sure surprises and mysteries will come. And then the last thing is just a pet peeve of mine. So this power bar, I just got this at a yard sale, right? APC, that's a well-known company. They make different kinds of power devices, backup power supplies and stuff like that. Surge. Hey, that was Skip. Hey, wait a minute. Hold the fort. Hold it. Hold the fort. The Skip is rolling. I'm not ready for it. So I did a CB radio just finished it a week ago, and I'm not ready. I don't have a proper antenna. Let me just turn the squelch here. The antenna is here. So I turn the squelch up. Only the loudest signals will break through. We'll keep monitoring. We'll just turn the volume down a little bit so they're not competing too much with me. Wow, that's great. I get such a kick out of that stuff because it is so crazy and wild and fun to listen to, I find anyway. So, and maybe in a couple of months, once I have my own CB antenna, goodness knows what that'll actually be. Maybe I'll be one of those voices. Maybe I'll be coming in down in Alabama. Yeah. Okay, so getting back to what we're doing here. Yeah, what was I saying? I think I was saying, right, that this surge arrest, which a lot of these power bars have surge arrest written on them. I got a lot of opinions about this, but basically they amount to what a waste and nonsense that is. And it starts with me working for a power company, and I can tell you, surges, there's lightning strikes. That's certainly a surge of a sort, but those are called lightning strikes, and protection against them is called lightning protection. It's not called, surge arrest. So, to be honest with you, what I think's going on here is people are afraid of nonsense. They hear this word surge. The guys who sell this stuff tell stories about, the surge is going to come in and blow everything out of your house. Anybody know where it's ever happened? Do you think a power bar like this was going to stop whatever happened in that house? So my experience on the power system, the only serious surge that was worth considering was a case, it would be an unusual case, where a high voltage supply line contacts a lower voltage supply line. The power protection fails to operate, so the circuits continue operating, and the high voltage is impressed on the low voltage, and then it goes, well, who knows where from there, right? So I even wrote a report in the company I worked in. where I suspected that, given the situation the way it was, that sooner or later a 600 volt DC cable conductor would contact a 120 volt three-phase conductor during some kind of failure, and that would put 600 volts DC into the downtown distribution system of Toronto, including 60-story buildings. I actually wrote that report and submitted it. And I don't know if the word chagrin is the right word here. That accident actually did happen about 3 or 4 weeks while my report was in circulation. That accident happened. Now fortunately, as far as I know, there was no surge, there was no conductor to conductor contact. Instead, the 600 volt conductor burned through a gas main and sent off a fire right in downtown Toronto. By the way, I posted a video on this. When this accident happened, all right. Okay, we're just going to turn the squelch a little bit higher. Bye-bye. When that accident happened, the positive cable, which are very, very dangerous power circuits. I won't go into the details of this, but let's just say the power doesn't go off. It stays on. 600 volts with thousands of amps. I'm too excited to listen to that. Thousands of amps behind it burned a hole this big through a large gas main like this. And now it had flaming gas pouring out the top. Oh yeah, I was saying I have a video because at the time this accident happened, at the moment it happened, a film crew was filming an interview just around the corner. They just literally, the cameraman literally turned around and shot the other direction. And actually, you can actually watch this accident take place in downtown Toronto. Unfortunately, someone gets hurt in it. That's what made the accident so serious. So, but that's an example of one circuit voltage being released where it shouldn't. And in that case, it was onto a gas main. But it could have just as easily been into another kind of power cable. There were other high voltage cables in that manhole, low voltage. It was packed with stuff right in the middle of downtown Toronto. Wow. So I really wonder, what is this all about? What have they done here that they can make this claim? They must have done something in here that they can make this claim. And surges, other than the kind I just described, which almost never happen, don't happen on the system. Okay, you're going to write lots of comments and tell me about the surge that blew your TV out. Another possible source of surges on a power system is errors being made by the operators of the power system. That's another possible source. And I'm not going to tell you about the gas company hooking up a gas pipe to a water main and then shooting water up an entire street in Toronto so it came out of everybody's stove. And yeah, I won't tell you about that mistake. So mistakes get made. Okay, let's get focused here. So what we're going to do now, we're going to look at a really interesting paper written by a ham radio guy about this capacitor checker. We're going to run through it. I'm going to run through every paragraph, and I'm going to talk about this capacitor checker and the very valuable information that this person put together. So why don't we just flip over to that now. Okay, so here it is. Notes on the Heathkit C3 by Ken Gordon, W7EKB. Thank you so much, Ken, for having taken the time to write this nicely written paper with all kinds of interesting information about the capacitor checker, which I have taken into consideration, maybe except for this very first part. So here he's talking about the voltage divider, the 22K resistors, and what the voltages and how they're labeled on the front and what they really are. They're actually not anyways near what the labeling is. So I'm going to check that on mine. I'll put a voltmeter on it. We'll just see what the voltages really are. This is for the capacitor leak test. He warns that this 47,000 ohm resistor that's really connected across the magic eye goes high. See, he found it doubled in the units that he checked. Well, I checked mine. It's 49K. That's fine. There's no problem there. So Nothing here to worry about. So here he's saying if you're going to replace one of those capacitors, you probably don't need the highest voltage rating. And guess what? That's exactly the conversation I had with myself about replacing one of those capacitors. Calculating true resistor values. So this is about that string of resistors and the varying voltages that it creates that you use during the voltage test. We're going to take a look at that. Here's a really, no, not this part, but soon an interesting warning is coming. Last 22K resistor and 450, which is only current limiter, so its true resistance value is not too important. Okay. Replace all the capacitors. Resistors in the voltage divider string should be replaced with higher wattage capacitors. 22 ohm. Make sure two resistors associated with the 1629 magic eye are within tolerance. He found his to be out, and that's very common. That there's usually a 1,000,000 ohm resistor associated with the magic eye that has often gone high. It did in the signal tracer, but in my capacitor checker, this resistor is fine. We're going to check this plate voltage on the magic eye. Make sure it's not way high, as he's suggesting. He did the line cord 3-prong plug and fuse thing. I'm not doing that. He shunted the power supply filter cap with 100K ohm. Now this is a common thing that is done to kind of put a little bit of a load on the power supply, and so that when there's very little load from the device, the power supply won't rise up in voltage. So it helps level out the voltage, makes it more regulated. There, I leveled out power supply variations. He had to replace his power transformer. I do not. So here's something very interesting. He's warning here that if you put a very large capacitor, look, this is 500 microfarads. Okay, this is a really large capacitor and a very high voltage one. So this size and this voltage, I don't think I've ever seen one like that. But if you get a big, huge dump truck like this, and you load the back of this dump truck up with charge, and when you let go of the leakage knob, the current, the discharge current from this huge capacitor is going to be driven through part of the main control. And this is unimportant unless you have a huge truck of charge waiting to dump back into this machine once the leakage is done. You got to do a big capacitor, you got to do it at high voltage. I don't do these. This is not going to happen. But it's an interesting warning that this extreme case, if you don't turn the main pointer control all the way to the left, you must park the main control pointer at the far left. When you do that, you can dump a large current through this machine and not cause any problems. If you have this control to the right, a big capacitor like this will blow a resistor out of it. So that's interesting. Not applicable to me. I'm not doing, I would be cautious anyway with charging up a big capacitor that high voltage. That's an awful lot of coulomb of charge in there at high voltage. You can kill yourself with something like that. Okay, so really all this amounts to now is checking out these voltages and the voltage on the eye. Let's go do that. And then we'll get into playing with the chassis voltage between these two guys. So this is still plugged into the usual place it's plugged in. So we'll switch it on, provided I can remember how to do that. I'll put it on 25, and we're going to measure the eye voltage first. I guess we'll do it with this. Now as we stand here, I don't know which pin it is on the back of the magic eye, which pin number should have the high voltage. But we'll know soon enough. Is it this one? Is it this one? 173. Could be that one. Or is it this one? 17. Or could it be here? 0. That's probably the ground going back. What about this one? That's kind of weird voltages, isn't it? Magic Eye's working just fine here. So the highest voltage I'm seeing on the pins back here, just doing them again, is 170. Huh. Those don't seem very, those are not very reassuring readings, actually. Let's just, why would I be concerned about this? The Magic Eye works fine. The whole unit is working well. Magic Eye's not under bright or over bright. I don't know how it would be over bright. The voltage is low. And Ken is saying don't go over 250 with them. Well, 170 is way off at 250. So don't see a problem with that. So we're going to leave the eye. Everything's fine. Resistor's fine. Everything's good. What we want to really do now is measure the voltage on these two terminals. See, these terminals are isolated away from the chassis. There's a small insulating ring right back here. .25 volts. Get in the habit of putting this where it should be. So is it really 25 volts? Let's put this on the 200 volt scale. Just like Ken said, it's closer to 50. Let me just put his values on my screen here. So he found, this is what he found: 45, 145. That's 150. That's dead on. 245. That's supposed to be 250. That's pretty good. 450, he found, no, this is 350. That's very good. And 450. So what he said is obviously the position labeled 25 volts should have been labeled 50 instead. And that's what it is. They made a mistake here. This should really be 50. In fact, when you look at the numbers here, you've got 450, 350, 250, 150. 50 would come next, wouldn't it? Not 25. So keep that in mind. That's all we got to do. Just keep it in mind that this is 50. What does it matter anyway? I have not been conscious of the fact that it's 50, and it's made no difference in anything I've done so far. So I think this guy's fine. Now, let's start fiddling around with the between the cabinet voltage. I'm going to bring the plug for this guy out where we can get at it. Okay. Now, on these outlets, let me just put on my other screen here so I can see what we're doing. So when you look at the three-prong outlet, modern outlet, you see one of the flat prongs is smaller than the other. The big one is the ground one. big one is the one they want to make contact first with, by the way. But the big one is the ground. So that's the ground side. Ground is a bad word to use. Let me clarify some of the language here. This is the terminal that in my house leads to the wiring which is connected to the neutral coming into my house. The neutral is probably connected to a ground rod at the pole in my backyard. Normally a ground rod is placed at the base of poles that have transformers on them, and for a couple of reasons. Some of it is worker safety. So when I say grounded, that's how far it is to the ground rod from here. Now there's another grounding that takes place in most houses where a wire is run from the neutral in your fuse box over as short as possible to the water service pipe coming into your house. A lot of people think that that's to make contact with an earthed electrode, which is your water pipe. There's some truth to that, but what it's really about is to make contact with all the piping in your house. Because the concern here is if you don't hook up the neutral to your water pipe, so you don't have that, and then somehow in your house, one way or another, a live wire, the black wire, the one with the 120 volts on it, touches a water pipe somewhere in your house. Maybe you've got a cable and a pipe in friction, and after 40 years, contact is made. So without the neutral connection, all that is likely to happen is your pipes in your house will now rise up to 120 volts. Some current will flow out the water pipe into the street, assuming it's all electrically continuous. In some cases it's not anymore. In some cases there's bits of plastic pipe here and there. But probably the fuse will not blow in your fuse box. That's the problem. The short circuit will remain in place until you find out the hard way that your house plumbing has now risen up to 120 volts. You will find out at some point, and it won't be pretty. So you put in the neutral wire from the fuse box over to your water pipe service. Now, if in your house you get the situation where a wire contacts your pipe, electricity will flow through the pipes, through that wire up to the neutral. It's basically a short circuit at that point. Huge current will flow, and the fuse or your circuit breaker will open and the whole thing will go dead. Every time you try to re-energize it, it won't. You'll call an electrician and he'll sort out what's happening in your house. That's what that neutral connection is really for. This whole thing about grounding it, or if you've got it in your head, if it's grounded, it's safe, just take a big black marker and just put a huge X through that notion, okay? Because that is not how things work. And every time you say grounded, in your head at least, review what you mean by that. In England, where people are a little smarter than North America, English fans there, they don't use the word grounded, they use the word earthed. So when you say earthed, I mean, that's pretty clear that there's something going into the dirt. So sorry to dwell on this, but this is really what this is all about here. We're going to sort out what's happening here, and to do it, we've got to understand what's happening in here. Okay, so I'm going to randomly, because there's no polarization, I'm going to randomly plug this in. Random. It's on, it's on. This is on now. Yeah, I can see the tubes lighting up. This will light up in a moment. Great, so first question is there already a voltage on the cabinet of this that we can read? Now, we got to go into a little bit of a discussion on meter impedances. So excuse me, so I'm going to ground this, oh, excuse me, ground this right to the electric system here in a very, very obvious way. At least I'm going to try. If I can't do it this way, many ways to skin this cat. Is this a good idea to have a screwdriver sticking up like that? You know, that's a little too loose. Let's go with something a little more certain. Some of you were probably freaking out at that. I will clip this onto a known ground terminal. So my meter is essentially connected now to the power system neutral in my house. Lots of things are hooked up to that neutral, all the steel cabinets on things, lots of stuff hooked up to that. So you often contact the neutral circuit in your house. Anytime you touch a water pipe in your house, you are touching the neutral. You should be. So first we're going to check right on the cabinet here. We're not going to do it with DC. That would be a folly. We'll do it with AC. Dingity dog. Now, so the question is, could I light a light bulb off that? If I put a light bulb between the cabinet and ground, would a light bulb light up? I'm sure the answer is no. 126, wow, that's the whole shot. There's nothing left. Let me flip this around. And did I say this power bar is just plugged into the wall, essentially, in my house? Turn it around the other way. So this is a bad indication. I would rather see like 50 and 50 up here, or something like that. Not all of it and almost none of it. That's not very reassuring at all, in fact. When I'm plugging these guys in to use them, when I'm putting them in, permanently into my shop, I go through the process you're seeing right now of figuring out what the best way is to turn these and plug them in. Okay, we kind of know the story with this one. Let's plug in the other one. And as soon as I can find the plug. Where's the plug go? There it is. Okay, again, just randomly, they're not in contact anywhere. Nothing is touching. Where's the ground wire here? Here's the ground wire from here. I'm going to put it back here where it will get into lots of trouble. I'll put it right here. I keep an eye on that. So it's not touching anything. We're ready. There we go. Now we're going to switch on. While that's warming up, I'm going to repeat the voltage test over here. I'm going to turn it off and see what happens. So we have low. If I turn it off, this is the hot chassis problem. This is the essence of the hot chassis problem. Now if I want to get rid of that voltage, I can just reverse this plug. Is it true? Is it true? But now if I turn it on, hot chassis. You can't escape it. That's the message here. It plugged in the wall, you can't escape it over here. You need, the only way to stay safe with these guys is to understand what's going on. If me turning this on and off is a mystery to you as to why this voltage came and went, you need to read up on this. This is the only thing I harp on in my shop about safety, is the hot chassis problem. Because that's the one that's going to get you, for sure. And you know what? There's never a time where I'm at ease with it in here. There's never a time where I'm at ease with it. Nor should there be. Okay. This guy should be warmed up now. Yep, magic eye is on. We'll do the same thing. We'll look at the chassis voltage. 102. So it's not full. It's nearly full. Nearly full. I'll reverse this now. So we're a little closer to the 50-50 thing that I would like to see, but not quite there. Now again, the question is, so there's a voltage here. So what? I get thousands of volts of static electricity on me, and I live through each day. My cats don't like it. The little static generators running around my house. So that's a good question now. So these are both plugged in for low chassis, are they not? What did I do with this one? Wore out my meter. No, he's plugged in for high. Let's plug them both in for low. With them on. With them switched on. Because the same thing will happen over here. When I switch this off, let's just check and see. I'm going to test all my theories here. So when I switch this guy off, this will go up to 60 or 70 volts. Sort of. Not quite. So the fact that this, reversing the plug is giving readings that are around the middle, around a half of 120 volts, tells me probably this guy's okay. But this one, I'm really getting a different message out of this. The message I'm getting out of this one is that this one's a little more dangerous. And I did get the shock. Moving a brush shock, putting my hand in between these two guys, which I won't do now, probably touching this and that. And I assumed it was coming from that. I just finished the restoration of this guy. But in doing all this, I'm not so sure the situation is good here. So voltage between them now. And if you notice, I'm using this meter. I'm not using one of my vacuum tube voltmeters or anything like that. That would be folly, because those meters have their problems, which I'm going to be dealing with next. So between them, like this, we should see basically nothing, I would think. Pretty much nothing. So we get 30. Let's turn which one off? Let's turn this one off. So again, if you think, with this hot chassis thing, if you think turning the radio off makes it safe, no, 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 no. Turn this one off. Oh, that should make it safe. We'll see what we get now. Now we're getting 24 volts. Again, I'm not really saying it clearly, but there's probably no oomph behind this voltage. And if I could find my little cheapo meter, which I really need to find now, I'm going to go hunt for it in my house very thoroughly. I think we'll find when I make these same measurements, the meter keeps saying 0. And the other question is, can you feel this? 25 volts, pretty hard to feel 25 volts, but if this is 120 volts, even with very little current behind it, yeah, you can kind of feel that. Reverse the plug. It's as if you can't escape this voltage. Now a couple other not so much safety issues, but just technical issues. Using stuff like this in your shop, if you have it set, you have the plug set so the chassis is running high compared to the neutral, and you go to use the instrument, you'll probably introduce powerful hums and other stuff into the thing you're testing, because of the different voltages between the two items. So if you so these are all things that we're checking out, again, because there's not a lot of oomph behind it. If you apply a common neutral, a common grounding wire through here, it would all go away. But doesn't it make you wonder what happens though if you were to ground these two things together solidly and then reverse one of these cords? You're not going to get a current flow between them. Blow a fuse? No, you won't, because it's all on the other side of an isolation transformer that's in each one of these. So each of these units has its own power transformer, and all the works are on the other side of it. As long as the primary of the power transformer is not directly connected to the chassis or not connected through a capacitor, the only way you can get these voltages on the other side is through some kind of capacitive effect going on. That's my belief. Okay, I'm giving a big speech here, but please, you should add a question mark at the end of just about everything I say. All these things, it's really important to get them clear in your own head and do your own thinking about this stuff, because it's complicated, and I'm not trying to lay out how to be 100% safe with all this stuff. That's not what I'm trying to do. I want people just not to be lackadaisical about these things. Sometimes I appear that way in my shop. Maybe lackadaisical is a little bit of a strong word, but I don't harp about these things a lot. I'm just working along. A lot of stuff's rolling around in the back of my head, that I'm not talking about. I think I've mentioned before, often you'll see I only have one hand out here. The other hand, I literally do put it behind my back. I literally do these things while I'm working in here. So since this is a little bit about safety, I guess I got to harp a little bit. So what do we got between these now? I've forgotten where we're at. Clip that on there. Okay, so we got 66 volts. Let me flip this one around. Neither unit is switched on at this point. So one of the problems in a shop like this that you can get from having this kind of scenario not cared for right, let's see if I can demonstrate it here. I'm going to turn on this big old radio up here. I'm going to set it to the AM band. It is already set there. The antenna from it here. It's not much of an antenna there, is it? Maybe I'll put a little clip lead on here. It didn't make any difference. Let's see if this will work. Just going to leave this here. It's just to pick up junk in my shop. What junk? This junk. It's a great demonstration of nothing. What's our voltage now? So we're grounded to this one. So we should put the higher voltage here. Just 1 second here while I get a lead. So using the high impedance meter here, and you're not watching. What are you doing? Don't watch up there. Watch down here. You didn't see the nonsense I just did. Did you? I was doing this. Expecting static out of the radio, but nothing came. Okay, everybody stand back. Now, can you hear that in the radio up there? So that's 65. Can't hear that. Voltage is probably low now. 25. Of course, watch what happens when I touch this. It goes away. So what I'm trying to demonstrate here is that if you're using these two instruments or instruments like this simultaneously, that voltage between them you can apply to the radio by accident. And what you would get is, well, who knows what you would get in that case. Lots of hums and stuff like that. You got to be thinking about this stuff. Before I did the restoration on them with bad capacitors and that, I was quite anxious that the voltages on the chassis were actually pretty strong stuff. Certainly doesn't appear to be the case now. I'm going to go find that little voltmeter. Okay, I managed to find it. 8-range multi-tester. So this is the kind of meter that got me through until I was about 21, something like that, as I remember it. So these are commonly battery testing meters, Micronta. Let's see, it says 2 joules, 2K per ohm, 2,000 ohms per volt. It's not particularly good. So 2,000 ohms per volt, if I put this on the 1000 AC, so it's 2,000 times 1,000, that's 2 megohms. That's pretty good. That's a lot bigger than I thought on that scale. Right? 2,000 ohms per volt, and the volt is 1,000, so it's 1,000 times 2,000. That's 2 megohms. Okay, this might actually work really well. Of course, when I was a young guy using this stuff, I didn't understand these things that well. Really. Oh, let's read with the real one. I shouldn't say real one, the digital one. So we're looking at 26 volts. Can we see 26 volts on this guy? So you probably can't see it, but the meter is lifting up about the width of a needle. Going around. Now we're measuring 50 volts AC with the high impedance meter. With the low impedance meter we measure. So you know there's something there, but it's barely moving the needle. Now if we put this on a 150 scale, now it's 150 times 2,000. What's that, 300,000? Times 2,000, 300,000. 300,000 ohms, so it's not as low as I expected, frankly. I thought it was lower. Well, let's take a look. That's still moving it up. But you're certainly not going to get what it should be coming up to around here. Is going to match that. The fact is, this is actually, in some ways, this is a better instrument to measure these, to do these tests with. You're no longer trying to really read voltage with them. You're really looking at how much power kind of can be pushed between these two units that would cause the pointer to go up. It's a little more like that. Power's not the right word either. So how high can we get this meter to go? I'll put it on the 15 volt scale. That's internal impedance now is 15 volt, 15 times 2,000, 30K. That's still kind of a big number, isn't it? 30K. So on the 15 volt scale, if you looked at that reading and tried to seriously use it, you would conclude that there was 0.2 volts or something crazy like that on this scale. You go up to the other next scale up. Now there's more impedance in the meter. The meter, about the same movement, but now it's a few percent of 150. And if they did it on the 1,000, you get the same kind of movement still. It's just working out that way. You get the same movement. Now you would say, oh, that's a few percent of 1,000. That's 40, 50 volts. That's pretty close to the truth, isn't it? And I guess that's what would happen, you know, as you, wait a minute, that's not quite right. 40, 50 volts on 1,000 volt scale. Oh yeah, that's right. That's 100. Yeah, it'd be just, yeah, maybe 20 volts there. Is anybody following what I'm doing? I don't know. I don't know if you are or not. Check again. I want to see that 120 there again. That's what I want to see. That's the one. There we are. Now it would appear that the whole line voltage is sitting here. So you can't tell the difference. If you read this kind of voltage, you can't tell the difference between 120 volts through a high resistance circuit and 120 volts straight from Niagara Falls. You can't tell the difference. This can help. This can help you tell the difference. So put it on the 150 volt scale. 150 times 2,000, 300,000 ohms. That's still really high. So aside from the fact the meter's not zeroed very well. So on a 150 volt scale, I would say that's a couple volts. But you know, it reads 120 on the other meter. It's interesting that that meter is changing. Now look, the lead here is open. Yeah, tricky to try to explain these things. I got an idea in my head, but I'm not going to try to explain it, why the voltage drops on an open meter. I think there is a valid reason for that. All in all, what are we getting here? So we're proving that there's no oomph between these guys, even when there's 120 volts there. That you can reduce the voltage between them to almost nothing by getting this right when they're operating. So now, with both operating under this condition, yeah, don't use this meter. We want the more sensitive one, but because we know what we're doing, or at least we think so, it makes sense to use this one. So there we are. But of course, as I've demonstrated, the problem is turn one off and you just get a different picture. So what are you going to do? You're going to, every time you turn them on and off, you're going to pull this in and out. And this voltage, I think you could still feel this. I don't think I can escape it. If I were to go between these, which I'm not going to do, I think I would feel it. Certainly on the back of my hand, I think I would feel it. Maybe not so much through my fingers. And so what this is really yelling out to me is the only way to settle all this down in my shop is to run a common ground bus throughout the shop and attach all this equipment only after restoring it, you see, to that bus. So these two are ready now. I know the story on them. I know how they work. I've tested the heck out of them with the outlet and all this kind of stuff. Let's go on. Let's do this first. Stop listening to that radio up there, chugging along. Our skip guy went away. Skip went away. Let's just check. I'm just going to turn the squelch here. Well, it's volume that went away. Yeah. They're still trying. Yeah, that's right. I turned the volume down on it before. Let's turn this guy off. The next thing I want to do, look inside this. We're going to look inside this thing. Take this out, and we will discover for ourselves what they got in here. It's a matter of pulling out 7 screws. Oddly enough. Did I unplug this? Yes. Double checking. Model number 1P, PER 70, product serial number, product of China. Underwriter list, Underwriter Laboratories. American Power Conversion, APC. Customer service, electrical ratings, 15 amp. Use indoors only. Caution. Teleline current limiting feature could be rendered inoperable if improperly installed. See installation instructions. Power tap. TVSS ratings. Bunch of numbers here. listing numbers, I don't know. Okay. Took the screws out, that should be enough, shouldn't it? I took almost all the screws out. They're loose. Holy schmoly! Okay, yeah, I better start eating my words here. There's a pile of parts in there. So, yeah. So this is here. He's going to fall apart here. This is definitely unplugged. I've seen the end of the cord. That's okay. Wow, let's not stop. Let's pop this out. Looks well built to me. Offhand. What do you think's in here? So this leads to these kinds of terminals here. Shouldn't be much in there in terms of power, should there? So this is a power supply for so there's one wire coming to it, the green one, which assumably is the neutral line. You can see that they've used the green as you would. The green comes up to this, the third prong bar, the neutral line. Connects to these two terminals here. Connect to these two diodes. These diodes are in a rectifier type arrangement. There's two more diodes here. Would do it look like fuses? Yeah, F2, F3. And then these guys in here. Wow, that's a lot of stuff. But what's it for? You know, like if you imagine the green wire going high because something has happened, power lines have, a tree has fallen on the power lines, and somehow you've now got this huge surge of voltage, high voltage coming into your house. So what? So what happens here? I don't know. I don't know what's going on there. Something to do with clipping the voltage, or the diodes preventing the the diode breakdown voltage being used to prevent the high voltage from that's now on the neutral because of a fault and traveling into here. I don't know. I don't know. I don't know. That's the most I can say. I don't know. How do we get this piece off? There. One screw. Gosh, there's a lot of stuff in there. Well, I better shut up from now on. I've been a bad boy saying stuff. So this looks like a great big fuse here. Yeah, F1. That's the fuse. This looks like a great big capacitor here. 1 microfarad capacitor. So this might be quite useful in reducing the amount of interference traveling, interference that's coming in on this, radio interference coming in on the power cord and then not making it out to these outlets, or vice versa, traveling from devices you're plugging into this, into the power cord. Well, I can't swear to what all these components. There's transistors in there. Wow. American Power Conversion, 1998. This is 20 years old. And to me, I'm looking at new technology. It's 20 years old. And let's put it back together. Okay, so there's a lot more to this. I take it back. I'm willing to bet, though, on a lot of these you could open them up, and you're not going to find this kind of stuff in them. This is definitely unplugged. Yes, I've seen the end of the plug. Well, there we go. Wow. Shame on me for thinking such bad things. I still question what the surge is. If the surge is coming from a lightning bolt striking the distribution system somewhere, and that surge is making it to your house, I'm not sure. I'm not sure what you can do about a bolt of lightning. Certainly on your antennas, if you're a ham guy or you're doing shortwave radio and you're sticking antennas outside, you should have a arrestor where the line is outside your house, just before the line comes into your house. This is squeezing everything down appropriately. Good. So I think I'll put that together on my own time. I don't think you need to watch me do that. So from here, what I want to do next is I'm going to put these back in their usual spot over here, and out is going to come this vacuum tube voltmeter, which I've also gotten the lift off of somehow, this small brush contact type shock. I'm going to bring him out, going to go through and do the restoration thing. I have some radios that are now winding their way towards my house, so when they arrive I'll be able to do some more work on radios, but until then I'm just going to continue with tuning up my own shop equipment. And a long overdue, that's what I want to say. So thanks a lot for watching, and see you on the next video.